is called induced drag. And typically, will just be D with the letter I on it, meaning induced. So it's extra drag caused by or induced by this downwash flow. So there's various different explanations. One, you can just think of it from an energy standpoint, is the kinetic energy of the vortex has to come from somewhere. It's going to come from the flow. And so it comes from slowed flow. And what slows the flow down and creates the vortex? Well, the wing does. So that's drag. Because the flow turns into this swirling flow instead of going smoothly over the airfoil. And that energy goes from the smooth flow into the vortex, and because the wing pushes on the air to cause that. And so you get an equal and opposite reaction on the wing from the air, creating drag. So the kinetic energy comes from somewhere, you get drag. Or here's a picture that helps describe it as well. So draw this big on your notes. You're going to have a big wing here. And draw d infinity. So there's the flow coming in, way out in front. And I've really exaggerated the angle of attack here for a reason, so that we can see the angle. You draw the chord line through here, through the wing, which would be an average chord of all the airfoils. Then that's the angle of attack. And if this were an airfoil, we'd look up that airfoil at that angle of attack, and we could get the lift. So if you have downwash, that's a downward flow velocity. And the section we're looking at is, say, out near the wing tips, the flow. So say this section of the wing out here, and this section of the wing out here is being impacted by the downwash. Get this downwash velocity W. So effectively, the flow you see is not straight across like V infinity, like the free stream flow, because you get this downward velocity. Now the air is not coming in like this, it's coming in like this. Which means the angle of attack that that section of the wing sees is reduced. Because the relative direction now is tilted downward because of that downward velocity. So you're just adding tip to tail. You get the forward velocity and then the downward flow. And this is what we call alpha effective, EFF. And this is the induced angle of attack that's caused by or induced by the downwash. So let's write some of these up here. Alpha I is the induced angle of attack. It's caused by the downwash. So it's a decrease in the angle of attack. So the alpha, you just look at the angle, it's the effective angle of attack, is the real angle of attack of the free stream reduced by that downwash angle. Yeah, and we call that upwash because it's not down, it's up. But yeah, if you get upwash from some other reason, yeah, it would increase the angle of attack. And in fact, for canard airplanes, one way to model the canard is to say there's upwash caused by the wing. So a big wing back here, and instead of having a horizontal tail in the back, which gets hit by the downwash, you would look at a canard up front and you'd say, well, there's some upwash hitting that. So that is a legitimate way that people model that effect. Next, let's draw the lift and drag vectors on this airfoil. So the lift with no downwash is perpendicular to the infinity. I'll write it on this side. So that's no downwash, and the drag is back this way, parallel to the infinity. But if we're hit by the downwash, then the lift and drag are perpendicular and parallel to the new direction. So we need to draw that. I'm going to try to draw it perpendicular. I'm scrunching things. Let me erase something to get some room here. So there's our lift, no downwash. So then the lift with the downwash is going to be perpendicular to that free stream, which is affected by the downwash. So there's the lift, the effective lift. And the drag tilts as well. So the effective drag, dotted line, that. And notice things happen now. Because of the downwash, we get a part of the lift vector acting in the drag direction. And the reason that's important is that our airplane is flying along this way. But the regions of the wing that get hit by the downwash, it shifts that angle. But we're still wanting to fly this way, so lift counteracts gravity and thrust counteracts drag for the airplane. But now, with the downwash, we get a little bit of the lift vector actually acting backward. And that's induced drag. So that's bad. Some of the lift that we'd really like counteracting gravity is pointing backward. And then if you look here, some of the drag is actually negative lift. It's in the negative lift direction. So that's another explanation. The kinetic energy comes from the flow to create the vortex, and that's where you lose energy, get drag. Or just physically, there's a component of the drag acting backward, or the lift acting backward, so you lose that. And then you lose some lift because this is downward. So just note that. Some of the lift is in the drag direction. Some drag is in the negative lift direction. So that's another explanation of what's going on with this. So now we want to be able to calculate this extra stuff. How much is the lift changed? How much is the drag changed? And because of our explanation up here, if you have small amount of lift, which means alpha is small, while you're flying at a low angle attack and low lift, that pressure difference is small. Is S. So if you have a small amount of lift, then the pressure difference here, low to high, is small, and you get a small amount of downwash. Whereas if you flip that around, if you have big lift, then you get a big pressure distribution, different. And so you get a lot of downwash. So the formulas that we're going to write up here are going to have that in there. The more lift you get, the more downwash, the more induced drag. What do they say? They don't like it? Can anyone see the board? Are they saying they can't see it at all, or it's just not good resolution? Yeah. They should be seeing exactly what you guys are seeing up here. Is it too small? Is the green? Okay, I'll do green. Thanks for the feedback. That's not what I want. I guess I can talk to them, can't I? I don't know what I'm doing here. Okay, guys, I want to write bigger and in black. See how that goes. So big lift, big pressure difference, big downwash. So the formulas are going to reflect that. And then the other deal is that if the wing is long and thin, then less of the wing gets affected by the downwash, because the downwash is only in the wingtips. So if you have a real short, stubby wing that looks like this, the downwash affects most of the wing. Whereas if you have a long, thin wing like this, the downwash only affects part of the wing. One thing I think, let me check to make sure it's running in high def. Should be. That's high definition. Okay. So if you have a high aspect ratio or high long wing, then you get an effect. So low aspect ratio, more induced drag, high aspect ratio, high induced drag. And so that's the formulas I'm going to give you that people have developed to model this effect. Got to be more. Oh, crap. There we go. That makes more sense. Makes a lot more sense, doesn't it? So that leads to this kind of a formula. The induced angle of attack caused by the downwash is directly proportional to CL, because then you get a higher pressure difference, and it's inversely proportional to the aspect ratio. And remember, the aspect ratio is B squared over F. So long, thin wings have a high aspect ratio. Short, stubby wings have a low aspect ratio. It's in the formula. There's my answer. You have to study circulation theory and the fluid flow around a wing and how it produces lift, and that's where it comes from. Kind of weird, isn't it, that the number pi shows up in there? We all know where pi comes from, right? I mean, the number is the ratio of the circumference of the circle to its diameter, right? But where the heck does the number e come from? Now, e to the whatever, it's exponential. I keep wanting to look that up, and then I never have time. Yeah, you can write sines and cosines as e to complex and real numbers, right? But why the number e? You do logs to the base e, right? But you can also do logs to the base 10. If I figure it out simply, I might come back and we'll talk about it. If you guys figure it out, I'll let you come up here and explain it. All right, so then the formula for the induced drag, same deal. It's done in terms of the coefficient. And notice the induced drag is CL squared. And this is for what's called an optimal or elliptical lift distribution. And what that refers to is how the lift is distributed over the span of the wing. That is, the lift falls off when you get near the wingtips and is biggest in the middle just because of the flow. But how this distribution happens there, and again, this will be an AE324 thing, but if you have what's called an elliptical lift distribution, that's optimal. But if you don't, then you put in a factor in the denominator that's called E. And this is called the span efficiency factor. And obviously E is 1 for elliptical, and E is less than 1 for non-elliptical. No, because E equal 1 is optimal, so you can't go super optimal, according to the theory. How are you guys on Zoom doing? Are you able to see better? Anybody chatting? The thing is too pixelated. Why is that? Oh, before I started writing bigger, maybe? I don't know. Let's see that. Yeah, it's better now. Okay. I'm trying. Keep reminding me to write big. So this is the formula you use, and then you're given E for whatever wing you have. So then here's how we calculate the total drag for a wing. So if we have a finite wing, here's how you calculate the total drag coefficient. You have the skin friction drag, which is due to the boundary layer. And then you have the drag due to the pressure distribution, meaning we have our wing or our airfoil, and you have pressure acting all the way around it. And remember, we had an aerodynamic force, and we broke that up into lift and drag. There's two components. So that's the pressure drag. And from the airfoil tables, that's where you get this whole thing. Yeah. Let me write that bigger. So that's the aerodynamic force due to the pressure distribution all over the airfoil. And you break it up into lift and drag components. And we drew that picture before. So this you get the airfoil tables. And then if you build a finite wing, then you add in the induced drag from that formula. And then if you're flying fast enough, you add in the wave drag due to the shock wave. And we'll do an example of this. I think we have time to do this today. Oh, yeah. So we're going to look at just a flying wing. We're going to look up that. We're not going to fly fast to worry about wave drag. Oh, and by the way, this part here is what's called the profile drag. That part, the airfoil table, the circle part, is called profile drag. So sometimes you could write the whole thing as C, D subscript P for profile. So now we have the tools to calculate the drag for a wing rather than just an airfoil. So that's what we'll do with this example. So here's a flying wing. Airplane. So it's just a wing. So I'm going to draw a wing because I always draw a picture. It's got a wingspan of 45.38 meters. And a chord of 4.54 meters. Area, the rectangular wing, so you can just multiply the two, is 206 square meters. And the aspect ratio, take b squared over s, is 10. The span efficiency factor, 0.95, so it's a pretty good wing. It's an NACA 4412 airfoil. Yeah, unless you know enough from 424 to calculate it. The weight is 7.5 times 10 to the fifth newtons It's flying at a density altitude of 3,000 meters at a velocity of 100 meters per second, so it's a low speed. So that means we don't have to calculate the wave drag. What else do we need? Oh, this, if you look up the density at this altitude, so we're flying in cruise, and so lift is going to be equal to the weight. Lift is up, weight's down. If we want to fly in cruise in steady state, that's what we got. So I need to calculate my induced drag, CDI, and I get this for that airfoil from the tables. So CDI is CL squared for pi E AR. I need to calculate CL. And CL is equal to the weight, which is equal to the lift, divided by Q infinity S. So I need to calculate Q infinity. So I look over and I get rho, which we looked up is 0.90926. And the velocity was 100, right? The dynamic pressure, punch that in the calculator. And that's newtons per meter squared, right? So pressure. So now we can stick that number up here. And our weight was a whole bunch. And then our wing area was 206. Sounds good to me. Thank you. 0.80. What was it? And what are the units? Yeah, there's no units. If you look at the meter squared cancels out, the newtons cancel out. So it's dimensionless because that's the way it was constructed. So then we can calculate the induced drag. We plug that into the formula. So CD induced CL squared, so 0.80082 squared over pi, 0.95 is E. The aspect ratio was 10, yeah? Right? So what do you get for that? So that's the induced drag. Now let's find the profile drag from the table. So it's a NACA something, something, something. 4, 4, 1, 2. So you guys have your book with you? Let's see if I can get the airfoil tables to show up on the Zoom. Yeah, so here's the drag polar. You guys are seeing that. How about the Zoom? Here's my mouse. Go back there for a second. Yeah, I want to see how it looks. That's the video theme. Yeah, the share screen I don't think will work because it's not going to share that thing. It's just going to use that as a video feed. Right, because there's no screen to share. Does it look okay? Because on my screen here, it's all dancing around. Let me zoom in. There we go. Now we've lost our axis. So what we have to do is look at the CL of 0.8. So let's find the line for that. So it's this line. Here, I'll mark it up here. Did I get the right line? Yes, that was amazing. So what's our drag coefficient? What should you say at this point? Yep, because what do we need to do next? We need to know whether we're looking at the circles or the diamonds or the squares or the pink hearts or the green clovers. Right? So we're going to have to calculate Reynolds number. How are we doing on time? We're good. So now we have to switch back to the screen camera. So we all know how to calculate Reynolds number, right? You did that on the previous quiz, I think. Yep, you had to. So it's rho, v infinity, c, the chord divided by mu infinity. We need to remember what mu infinity is. because we're working in metric here. So 0.90926 kilograms per meter to the third. The infinity is 100 meters per second. And the chord was 4.54 meters. I don't have written down here the units on this, but they've got to cancel out those. You guys have the mu units somewhere handy? It's in the back of the book, right? Meter per second. Like that. So what's our Reynolds number? Remember CL of 0.8, because we got to look that up on the chart. What did you get now? 2.23, right? Okay, back to the table. Back to the chart. What do we use? Well, all we got is 9 million. But we're at 26. So we're going to use 9 million. If you really want to do this right, you'd read the 3 million, the 6 million, and the 9 million plot points, plot them versus Reynolds number, and extrapolate out and hope for the best. You could do that, right, if you want to get a better number. We're going to use 9 million. So we need the diamonds. Okay, so what's our profile drag? Because that's the whole point of all this stuff. Is I'll switch back to the board here in a minute, but everybody take a minute and read off the diamonds and give me a profile drag. Everybody got it in their head? Write it down on your notes. Fold it up, pass it in, we'll do a secret ballot. No, just write it down on your notes. Got a number? Let's go back to the board now. What this other number is? Same deal. So what did you get for that? I'm going to start us out. What did you get? Another 0 and a 6 and a 5? Nah, because we can't read that accurately, right? It could be 6, 4, 6, 5. It's hard to tell. So we're at plus or minus probably 0, 0, 0, 2 maybe. So that's what we add to the, this was the induced drag. So the total drag is the sum of the two. Notice that how much induced drag we get for this plane flying at a CL of 0.8. Because that's what drove it, is this number here makes it big. So again, the lower the CL is, the lower the induced drag. We're actually flying at a really high angle of attack, producing a lot of lift. And so we get a lot of induced drag because that pressure difference is really high, producing all that lift. So we have to add the two together. Profile is 0.0065 plus 0.02149. And that's our total drag for this airplane. So let's say that we wanted to fly our airplane from here to California. And we wanted to do it on a small amount of fuel. What could we do to get less drag? Fly higher so the density goes down, right? Is there anything else we could fly slower? So really, you guys are all looking at this because the weight is going to be the weight. It's stuck. That's how much we want to carry. Yeah, so you can go on a diet. Can't change the wing area unless you want to start chopping pieces off. So we could fly slower. And that would actually feed into the fact that we're going to have to multiply this. The total drag is CD times 1/2 rho V squared, right? So going to crank that up, but we still like to get CD down. What else could we do? Fly with less weight, because that's going to get us less CL. And notice, wow, there's suddenly a trade-off, because here's V squared that's going to make the drag bigger, and here's V squared that's going to make CL smaller, that's going to make CDI, formula's gone smaller, right? So actually, there's going to be an optimal point between velocities. Higher velocities will give you more drag, and lower velocities will give you more drag, and there's a sweet spot in between that you could fly at where you reduce the induced drag, but you also reduce the drag here. So you get a balance between the induced drag and the profile drag. And we'll talk more about that when we talk about performance of airplanes. Yeah, so that would be your best cruise speed. And if you said, well, my airplane flies too slow at my best cruise speed, what do we do? You buy a different airplane. Or maybe we change the wing area so we don't have to, we have more wing area that gives us more ability to produce lift, but then you get more drag from the wing area. There's a trade-off there. So designing an airplane to fly at a certain cruise speed is it's an optimal optimization of design in what you're doing. All right, so that's how we calculate the drag and include the effect of the finite wings, which we have to because we can't build it infinitely. And we're out of time, so let's stop there. Let me point out, though, that there is a bit of an approximation in what we did because the CL value, the 0.8 value, was for the whole airplane. And yet we went into the airfoil data to read off the drag, right? So in reality, we have to go to each airfoil section in the wing and look at its local angle of attack and look up its own drag and then integrate over the whole wing. But that's beyond what I really want to do in this class. So this is an estimate of the drag. Pardon? Yeah, you guys, this is the intro to class. This is not the solution. Okay, guys, have a good weekend. See you on Monday. Let's see if I posted the next homework set. I haven't, right? I don't think so, so I need to do that. Yeah, I'm going to be looking at the schedule. I need to look at what the problems are and whether we've covered, when we'll cover the material. I just didn't do that. The earliest it will be due is Wednesday, meaning we'll go over it on Wednesday and it'll be due on Friday, but it may push back from there. I don't know. You too. Trying to figure out if there's a custom preset I can do. Doesn't look like it. It'd be nice to get something zoomed in a little bit more than the one we were using. See you guys.